you want to run such complex systems like radio telescopes, you need also a method to monitor parameters of the telescopes. And therefore, you collect a lot of data, thousands of data per second, and these data must be organized, must be evaluated so that you get alert states, and therefore you need a method to collect and also to manage large data sets. And therefore you need databases, not also for monitoring systems, but also, for example, for the organization of the orbits for the laser ranging system, so that you can get a direct access to the next satellites which must be observed. So therefore, we need databases, we need methods to access the data, we need a language to access this data, and therefore, welcome to the next lesson about databases.
Welcome to this lesson. This time we want to talk about databases. Databases are quite important because they organize data in a very, very flexible way, and they offer a very fast access. They offer search mechanisms, and therefore, if you have large data sets, like for monitoring systems or for other meteorological systems or whatever, you always need databases, and they also have a nice language, or with a nice language like SQL, you have a very simple access based on a view of data sets. So therefore, databases are quite important, and today we want to have a look into these structures. So today we talk about things like what is a database. So we already saw the background of databases, so coming from the file systems to a better organized way to have data in files. Then we have a look into different database models, because there are different, let's say, techniques or structures behind. Then we'll focus on to relational database models and its design, because most databases today are still relational and not so much object-oriented. There's a mixture, it's about 50-50 or something like that, but relational model is still a very important model. And then we will have a real practical view into the data access language SQL. So let's start with what is a database. Do you remember? As I started the lessons about data organization, we already saw these images. And again, a database is a structure, technique, where you combine data which are related to each other into file sets. You manage it with a management system, and you have a structured and standardized access method. So what does it mean? You have a lot of users, and these users have different applications here, so that different applications request data, and they also send in data over a predefined standardized interface into a managed system. And this managed system organizes the files which are behind, maybe with this ISAM method or other key-based techniques. So what is a database? A database has three elements. So you find them here. You have a data stock, you have data which are logically dependent, you have an administration possibility, and you have an interface, a standardized interface. So these three things, data stock, administration, and interface, are the most important things for databases. And if you look into this, you already heard about mechanisms to change or to request data from the databases. They are called data manipulations, and there are three different types, where the third one is just a combination of these two. So the basic thing, and what you always do if you send some requests to a search engine, for example over the internet, is this one. So you request data, you read data, it's just reading, and you request data according to a special key. You want to know additional things which are related to the key, or you want to get all of the data which you can find in combination of two keys or something like that. So you just request data, you just ask for data. This is a query. And then you want to change data. For normal internet requests on a search engine, it's not relevant for you, but the search bots and things like that, which scroll through the internet, use this. And also in a normal database system, in let's say in a company, you'll have also these changing mechanisms. So you have updates, you have inserts, and you have deletes of existing data. So what does it mean? You want to read the existing data and you want to change it, you want to update it. So these techniques are called mutations because they change things. So there's a propagation to the future. And if you want to read and if you want to change things, then these reading and changing must be uninterruptible. What does it mean? You read and you change, and the operating system or other interrupts, for example, incoming new requests, will not influence the whole progress here. So therefore, this combination must be separated or must be combined in a so-called transaction. A transaction is nothing more than let's say critical section of databases. So you ask for data, then you block this, and then you change it so that two accesses will not have some influences to a wrong, or will not have influences to get a wrong result. It keeps the integrity. And therefore, as you have different mechanisms, different possibilities to work with databases, you have also different roles. Do you remember? This structure is UML. So it's a use case diagram from UML. If you don't remember, go back to the lesson about the software design techniques. So if you think about which, let's say, actors or which scenarios you have with external users to your database, you'll find two possibilities: an administrator and a user. A user, so let's start with the simplest combination, or the simplest access point. A user just wants to manipulate data. He or she wants to query data and wants to update, delete, or add data. So the manipulation is the most important thing. So therefore, the selection, the update, the deletion, and the insert of new data is the most important thing. So this is the simplest standard way. And then you need somebody who is behind all of this stuff, who can create a database, the whole, let's say, from hardware to storage, all of these things, and also who controls and administrates all of the things behind. And therefore you need also an administrator. So these two roles are quite important. And therefore, an administrator can do the installation, also hardware and software things, and he or she can control and administrate things. So what does it mean? It depends on how you structure things, but usually you split it into these two pieces, or into these two user actors. Sorry, and then an administrator can create tables, can alter tables or drop tables. So this is the same what you can do here for tables, for the general structure of tables. And then you can also create search keys, which means indexes, and you can also grant rights, so that different users, remember the image before, different users with different applications have different rights. So it's not necessary, for example, that an administrator for personal stuff in a company has also access to the budget of the production, or vice versa. So there are sensible data which you would not like to have everywhere in your company. So therefore, these two roles must have two different, let's say, structures also in the language, in the access language, and therefore you have always this data description language part, and you have this data manipulation language part. And SQL supports both of this. So let's go to the next step. Let's have a look into which databases you find. So which models are currently available. And there are different techniques also in the storage mechanisms. So a very historical one, which is not yet anymore available, and therefore I will jump very fast over this, is the hierarchical model. Do you remember which technique is quite fast in search mechanisms? If you create trees, and therefore search trees, or the pure structure of search trees, is here the big background. So there was a very complex programming. The changeability of structures is difficult because you have always to create a balanced tree, things like that, which is not just, let's say, virtually a balanced tree. It's also necessary that the data are organized like this. So it was a historical setup. Also, more or less historical was the network-based technique. So if you remember, if you have trees, you can come directly to the next jump, that you have just graphs, and you connect everything to everything in a special way. So it's also very, very complex in programming. You have a very reduced redundancy, which is quite good because the data are just once in your system. But it's very complex in the structure. Also, updates and changes are quite complex, and therefore you win a very short access time, so that you have just a walk through the graph, and you will find the results. So these historical models are not available anymore. You have it in let's say own programs. If you do the programming for yourself, you have structured lists or something like that, which are comparable to these network-based or hierarchical structures. Nowadays, you have mainly two main models. One is the relational database model. A relational database model has a view onto the data like Excel. Excel is no database. Don't mix this. But the structure of the databases is similar to Excel. Everybody can use Excel. So it's a quite nice and simple way. If you have a table, you have X and Y, you have rows and columns, and you arrange your data there. And if you arrange also keys into these lines, it's quite simple to find the whole stuff from a line if you just search for one key. So therefore, this is a very simple technique, and therefore the structure of tables where you have a key combined with, for example, additional information, and where you have connections between two different tables, where you just have an additional table which has a new key and combines just the keys of other tables. so that if you search a combination between this and this, for example, which student is a participant of which course, so that you have a table of courses and a table of students, so here, and you combine it with an additional table, you have a very less redundant setup, which is very, very nice structured, and which is also or which gives you a very nice overview. So therefore it's very easy to program, because it also is supported with a special language. So the programming language is more a data manipulation language, as you have seen before in the UML diagram. The dependencies between tables are described again with relations, which are again nothing more than tables. So the structure of connections between different data is again just a table. So it's really nice. So you just think in tables, and the access time is quite fast if you search exactly for the key. Remember, if you don't have keys for everything, then only if you search the key, this is quite fast. If you search this information, you have to do it sequentially or with other techniques which increase or which reduce the access time, binary search, things like that. But you have to do it, you cannot directly jump to this position, because only keys can be searched directly. And therefore, it's a mixture of, let's say, runtime efficiency. If you have to go through a lot of these tables, and if you have these joins of different tables, then it's also not so fast. So it's also sometimes a problem that you, how should I explain it? You can always create a structure of tables, and you can always combine it, but in some cases it's easier if you have redundant information, so that you have a fast access. So it depends on, you should avoid this in the relational model, but in runtime scenarios it's much easier or much faster if you have these redundancies, and therefore you will still have some redundancies. Okay. Another quite familiar technique and a quite often used technique nowadays, all relational, or the most relational database programs or software suites also support the object-oriented databases. Therefore, another very important thing is the object-oriented database structure. It's very, very related to that what you know from the programming languages. Jump back to the lesson about these programming languages, where is a short explanation. What you do is you try to find generalizations. So you have a table which is the generalization, and then you inherit the information from there. For example, you have a table which is a table for person. Person has a name, family name, things like that. And you can now have special, this is the generalization, and you have specializations which inherit these things. They add additional information, so the table grows. It's like with a class in a programming language. So there's always a growing information, the attributes grow, and therefore you have the same here. So a professor has, for example, a title, or a professor has special additional information like the office number, the room numbers, things like that. You can combine this again, and you have also students, and you have special additional information, like here again you have name and first name, and you add here additional attributes like matriculation ID and semester, things like that. And then you can connect them also to other things, like what you know with the relational database tables. You have also here available a student, for example, has a list of courses. So it's very comparable. Objects are in principle records of the same type, and they are defined as a class. The data are encapsulated as private, shared, dependent, or independent, and protected. So you have the same structure, or a very similar structure what you know from the programming languages, which are object-oriented. You have inheritance, combination of types as tuples, lists or sets are possible, so that you have different possibilities. It's sometimes quite complex, like with the programming languages, so that most of the programmers don't really program object-oriented. They program a mixture of, let's say, sequential or functional programming, structure programming, and object-oriented, because it's a paradigm change, and here's also a paradigm change between relational and object-oriented. But both are very familiar, very well known today, so that these things are used. So they're very common databases in this style, and here I combined a little bit the different companies or programs. So relational databases are Oracle, PostgreSQL, MySQL. Very, very famous in the open source community is PostgreSQL, and very, very famous in the web community is MySQL, because it's a very, very nice, simple access technique. Object-oriented databases are My Object-Oriented Database or ADB. There are several others. For example, Postgres supports object-oriented styles. It depends on. Then there are special databases, which are not really relational, but they combine things. A very, very famous one is the XML database, like Oracle XML or Base X. They use XML files or XML structures. We'll see later in one of the lessons what XML is. You just at this point now, it's compared to TML, sorry, to HTML, which is used for the programming of browser web pages. XML is a tag-based, markup-based language, and it structures it more or less, again, hierarchically. It depends on, it's not so fast, I would say, but it's a very nice technique to structure data. And all files are directly readable, because all files are accessible. They are not, you don't need special programs to read it. You have a very standardized way also to find paths in this XML document. Then you will have things like time series databases. If you remember that, for example, the first search, or if you search one item according to a key, this is quite fast with all of the key-based techniques, because you try to convert the key directly to the index or to something what is an address. This is quite fast, but the rest, if you have then a sequence of data, so like a time series where you find the first entrance point and then you read the whole day, for example, of data, then you have the situation that the reading is again something like a sequential walkthrough. Therefore, there is no huge, let's say, impact into runtime if you do this. So it's quite fast if you search single items, but it's not so fast if you search continuous data. And therefore, there is a special method which is used in time series databases, like InfluxDB, where it is focused on a very fast access to the sequential data or time series. And then you can also have special database files like SQLite, where you have a program library which arranges files in a special search technique, so that you use this library instead of the basic file writing and reading techniques, and therefore you have a SQL database Lite engine library, which is something like a database, but it's not really a database. It's just the organization of single files which are quite fast and accessible by keys. So these things are at the moment on the market. So there are also several other small things, but the most important are the relational, the most important are the object-oriented. In some programming environments, you have this InfluxDB or also SQLite things, but focus should be on relational and object-oriented. And as I think the simplest approach is the relational technique, we will focus now on the relational database model and also on its design. So what is a relational database? We already saw that it is constructed with tables. So what is a table? A table has a name, like here students. A table has columns, which are called attributes, and a table has lines or rows, which are called records or tuples. The first column, mostly just one single column, but you can also combine two columns to one of these keys, are called primary key. So therefore you have a very specified attribute, which is the key, and you have the rest of the attributes which you can find if you search for a special key. Now you can think in all possibilities. So like in Excel, you can write more than one information in one element. You can structure it as you want, as long as the dimension will fit. It's quite nice, but it is not so helpful if you have information redundant or if several information can be found under the same key, so that you have to search again sequentially, for example, the content of one element or in a record, and therefore you have to follow a special standardization, and this is called the normalization. So therefore the relational databases use normalized tables, and they consist of a head with attributes and a body with records, which build a mathematically describable data set. So it's really a data set like it is in math. And they have to follow the following things. The records are unique, so each key appears only once. So each record is unique in this table. The records are not ordered, so it's not an ordered list, so we have to use other techniques to directly jump to the idea. Ordered means in the case of the top view, in the recording on the file system, it depends on the database system how it is done. The attributes are not ordered as well, so you can also change the columns. And the attributes are atomic. Atomic means that you don't have a list of elements in one single, let's say, column element, so that you avoid sequential searches in this table. And therefore you have to follow a standardization model. And the standardization model of tables is called normal form. You will find a lot of normal forms. I will focus on 3 special normal forms, because if you're a beginner, you don't have too much benefits of the other special forms. The most benefit is in the first 3, let's say, normalization steps. The first one is just use one single atomic element in each table element. So attributes consists of just one atomic value. And then non-key elements are fully functional dependent from the whole primary key. What does it mean? If you have a record, all of these elements in the record should be completely dependent or functionally dependent on the key. So with the key you should have a direct connection to the rest, and this is also a very important thing, so that you don't mix data sets which are not really completely dependent. So if you have courses and students, you can have one list, but then you have a mixture. And the big important thing is that you always think about redundancy. So all of these steps avoid redundancy. They avoid search. They create search structures, but they avoid redundancy. And therefore, all of these things try to find this. And therefore, the third normal form says that non-key elements are not transitive dependent from key candidates. So if you have a record again, and for example, you would have a second column where others are directly dependent on this key, and this key is dependent on the first one, then you see that there's maybe a mixture of data sets again. So therefore, we focus onto these three techniques. So the first one is quite simple. Here at this table disposal, you will have a list of elements, and you split this list of elements into single atomic elements per record element. So what does it mean? You have the ID again, but then you don't have a vendor ID, which directly contains the list of all products the vendor offers. You have now a vendor ID, which is unique to the vendor, and according to the vendor ID, you have the product, and this combination, this connection between vendor ID and product is now a new key, which is the product vendor, for example, ID. The vendor ID now can also be used in another table, for example, to explain the vendor, for example, the address of the vendor and things like that. So this is the normal form, the first very important normal form. If you do this step, you have already a huge jump into reducing redundancy. So if you have a list with atomic elements, this is the first normal form. The second normal form is that the table must be in first normal form, of course. So it's a nested set of normal forms. And all non-key elements are fully functionally dependent from primary key. So in this case here, it's not that, for example, the title of a course is completely dependent on the original search key. So you have here the course title and the course ID. So there is a functional dependency on the course ID and the title, but there is no functional dependency between the name of a student and the title of a course. So you have these blue arrows show you functional dependencies. The red arrow shows you where you don't have this functional dependency. And you see it again if you watch a larger table with already inserted records. You directly see that you have redundancy there. If you start with empty table, so if you design the database, and especially as a beginner, you will see, you won't see this, but if you fill data in, you directly see each time if you have a redundancy in your table, you have not really a given normal form. So what do? You split it into two tables and you create a relational table. So you have a table with students, you have a table with courses, and you mix this with a relational table. So you have already seen this before. And then third normal form tells us that the table must be, of course, in second normal form. And non-key elements are not transitive dependent from key candidates. So here we have, for example, student mother. And student mother, we have Smith Betty, Smith Martin, Smith Noemi. And the mother is always the same. So again, you have this redundancy. So what does it tell us? So we have a functional dependency between the birth name and the first name, but we have only a transitive dependency between the birth name of the mother and the student ID, or the ID of the person who is the child of this mother. So there is not really a strong dependency on that. And you see it directly here with this let's say, redundancy setup. So if you have filled tables, it's often quite easy to understand why this normal form must be created. But if you start with an empty table and you just design the database, then you don't see it directly, and therefore you split it again into two tables, and therefore you have a table, and the combination is now not a relational table. The combination is now just the key, because you assign the key, for example, of student mother into students, where the key, the primary search key, is a foreign key in another table. So in this case, you have a table which is directly connected with the key, which is an attribute or a column in another table. So if you have this, it supports all of these set combinations, all of these usually known mechanisms to join or to intersect or to calculate differences of data sets. And therefore, if you do this, relational database is a collection of variable data sets structured with a logic view on the basis of tables, which are possible with a possibility to define relations between dedicated tables. And you can follow the following operations. So you can make an union. So what is a union? Union is you have a dataset 1 and you have a dataset 2, and you have, as a result, the whole combination of this. It's not so often in databases. Much more often is this. So you have an intersection. In the section you have a dataset 1 and a dataset B, and you search the common part. So you search things which appear in the one and in the other. This is often used. Then you have a difference. So for example, you have dataset 1, you have dataset 2, and the difference is that you have just the rest, which is not part of the database or of the dataset 2. The Cartesian product is also sometimes used in relational databases. So you have a dataset 1 and a dataset 2, and you make all combinations. So AX, AY, BX, BY, CX, CY. So that the resulting product, or the resulting Cartesian product here, is now a result of all combinations. Sometimes used. Very often used is the where condition. The where condition selects single records according to a key. So you search a special key and you get all of the data. So for example, give me all data where the student ID is 1250. Okay. Another very important thing is, if you have this where condition where you select records, you can of course just select special attributes. If you are not interested in the, let's say, address of a student, but if you're interested in special information, if it is female or male, for example, or if you're interested in the combination of IDs and names, things like that, then you just select special attributes. So you have this projection. Here it's called restriction, here it's called projection. Also often used is the natural join. The natural join is something like this with this relational table. It's very similar. So this natural join has two data sets, and it uses a combination where you join these two tables. So for example, that you have a combination of, here's A and Y, and then you have a combination A, Y, N. Or you have B and Y, and then you have B, Y, N. Or you have CX here, and then you can combine with this CXM. So if you check this, it's very similar to this, what I explained with the third normal form things. So that you combine according to a special setup where you have special information which you search in the second one. So this is the natural join. This join, this projection, and so here, and also, sorry, here, the restriction, these things are our daily bread. So it's our daily work, okay? And then you can also have a division here. Sorry, it's here. So the division, you divide one data set by the other, and what you get is just the result where you have both here. So X and Y is for A available, and therefore you get as a result the A. Is not really common in databases. So with this information, we can now start to design databases. We can now start to design relational databases, and therefore there is a model which you use. And there is a general approach that you should avoid these redundancies. This is the difficulty. If you start with an empty table with, let's say, a white sheet of paper, then it's quite difficult to directly see the dependencies. But it's very important that you reduce these redundancies, or that you reduce these dependencies in one table, so that it is possible, and you create a functional dependent, let's say, structure where everything is dependent on one key and that you have no redundancies. So there is one problem, that the design is very individual. So if you have two database designers, you will get two different results sometimes. And it depends on a huge knowledge base of experience. So there's a special style. And to avoid this, or to really explain what the database or how the database looks like, there is a model which is a graphical model, again comparable to UML, so it's standardized, and it's called Entity Relationship Model, ERM. This entity relationship model is a very, very useful tool to show in a graphical way dependencies, relations, and also the content of, or the structure of a table, not the content, sorry. So how does it look like? In principle, you have to describe the tables. So what does a table have? A name, like your students, and attributes. And you have one special attribute which is the key. So therefore, you have to describe this. You describe the table with this rectangular block here, and the attributes are described with its ellipses. So you assign it with lines, and you have one special attribute which you underline, so that you have a key. You can have more than one key, of course, so that you have key combinations, but that's it. So the same with the other tables. And then you can have direct combinations, this normal form 3 thing, where you just have an additional column, which is a foreign key, pointing to a primary key of another table, or you can have these relations between. So these relations between are again tables, but they just contain foreign keys. So they just contain foreign keys, which are primary keys of other tables. So they combine primary keys in a table so that they are called foreign keys. You have these two possibilities. You have a foreign key directly as part of a table, so that you have a direct connection between one table and the other, or you have an additional table which combines the foreign keys. It's similar like a join. And then with this relation table or relational table, you can define how the relation is. So if you have a 1 to n, a n to 1, or an n to m relation. So for example, one student can participate in several courses. But on the other hand, one course in combination to the student is just visited here, for example, by this one student. But a course, of course, can have several students available. So you can define how this connection is made. So therefore, we have to discuss these relations. There's a 1-to-1 or a very specific 1-to-0 relation. I will directly explain it. A 1-to-n or a m-to-n or n-to-m relation. So what are the differences? So a 1-to-1 relation or relationship is that you have a foreign key in a table which points to another table where you have additional information. This additional information can be or not, so that you have this 0 record. For example, a sample is a title. So not all people have titles. You can have this available in an additional column, but another thing is you should avoid empty or null columns. And therefore you can create, for clarification, for simplification, an additional table where you have a primary key pointing to doctor, professor, or whatever, to the title, and then you connect it with a foreign key to the individual person. So it's a 1-1 or 1-0 connection. A 1n relationship is that, for example, a specific or one single record in one table can have several dependent records in another table. So a sample is a mother and the child. Each child usually has one mother. So there's only a 1-to-1 connection, but a mother can have several childs. So remember what I showed before. So the family name of the mother, or things like the birth name of the mother, things like that. So it directly fits to here. So each person has one mother, but the mother can have several kids. So it's a 1-to-n connection. An m-to-n or n-to-m connection or a relationship is that one specific record in one table can have several dependent records in other table, and vice versa. A sample is these university courses and students, where you have this relational table. So the first two tables have just foreign keys. The first two relationships have just foreign keys in their own table as a connection to a primary key in another table. This m-to-n relationship is the only relationship where you have an additional table where you combine two foreign keys pointing to primary keys in other tables to a new scenario. So for example, a student can be in different university courses, and different university courses can have different students. So you have this combination of NM. And here's again the NM or MN relationship with this additional table where you combine just foreign keys. You have already seen this in the slides before. It's just as a reminder to that. So the entity relationship model on the left side explains exactly the tables on the right side. So you have this combination, and you can of course assign also additional attributes to the relational table. So for example, you can have two foreign keys and an additional information which explains the relation in another way, for example. For example, you can have the final result as an additional column in this relational table, because it directly connects the student with a university course, and you have one single entry for each course in the relational table of the students. Okay, so having a look into a large database. So here for the satellite laser ranging, I used exactly this setup, a little different graphical representation, but it's a real database for satellite laser ranging systems here in Wetzell. And you have, for example, explanation for targets. The targets contain attributes, which is the first part. You have types of the attributes. You have a table name, and you have also additional constraints. I did not explain this yet, because you can also say that, for example, an attribute, so a column, is not allowed to be empty, or that a column must fulfill special constraints. So it must be from a set of other values, for example. So this combination, and then the lines between the table are the combination in foreign keys to primary keys, and therefore you have here a large database structure which really represents this relational database model. Okay, the final things what we want to do is now related on a more or less practical part. So therefore I will sit down and we will have a look into a sample which you can directly run on the computer, on a browser. W3 Schools offers really nice utilities, and you can directly train the input with live real-time checkers. And therefore we will now do this. We will now focus onto a new language. I think you will not have heard from this, but my experience showed that you will have contact to databases in your future. It depends on more or less, but all the time it's quite important and quite helpful if you already know the SQL language. SQL, or SQL in the original nomenclature, is a structured query language. So SQL stands for structured query language, and it was programmed for the access to databases, especially relational databases. The history goes back to 1970, and there are several different standards. Now it's also possible to get object-oriented elements in XML exchange. It's a non-procedural, more data set-oriented language, which tells the database management system which data are needed or should be changed, manipulated. The advantages of this is that the user does not have to know programming language in a case of writing for loops to get all of the data. The user and programmer just uses a very powerful, as I said, set-based standardized access method, and must not know anything about the data behind or how they are organized. So it's the focus is really on sets, and therefore it's a really helpful and nice utility. As I said, you can use the tutorial. Also for the tutorial you will need this W3 Schools part here. So there are several other HTML and XML and so on. We now focus on SQL, and you can directly use this. There are other possibilities like SQLite online, which you can use, but I will show the next steps with W3 Schools. So let's start. How does a SQL statement look like? There's one way to represent reserved words. It's not case sensitive, so you can write it as you want. Take care on some special representations like some databases require lowercase and uppercase separations. MySQL, for example, but in the general SQL standardization is not required. But there is one general, let's say, definition that you should write the reserved words with uppercase. So it's like a normal sentence. What do you write? So in this case, you can really easily understand what happens here. So create a role. So it's an administrator command or an administrator SQL command. Create a role called Alex. It uses an encrypted password here plus Alex exclamation. And then you have some attributes to the user Alex, like super user, no create DB, so that this role is not allowed to create a new DB, no create role, they cannot create new roles, no inheritance. There is a possibility to log in, and there's a connection limit of 100. So it's a very simple structure. You have to learn, of course, these things. So I start with the administrative things, which you cannot test in the W3 school because the administration is done by other person, but it should show you that also for administration you have the same structure of commands. So creating user roles is a administrator command, and also creating a database. So a database management system can have different databases. Do not mix this. So different databases mean different data sets which are related or belong to each other. So for example, you can have a database for satellite data, you can have a database in parallel to stuff at the observatory, for example. And therefore, you have to create this database which is in the same database management system and with the same access point, for example. So here the creation of a database follows the same structure: create database with the name my test with the owner Alex. So I created a user and I created a new database with an owner. So you can have different other access points so that the users have access to this. Then all of these things is part of the administrator. What we now do is directly jump into the possibility of a normal user, and a normal user should be able to create tables. So the designer of a database itself is a user, maybe also a special administrator, but he should be able to create tables. And therefore, creating a table looks like this. Again, the same style, create table. If I go back, you see the same structure: create database, create row. It's the same structure. You can read it like a sentence: create table students, and create table students with the attributes ID, the type integer, and if it is a key or not, or a special constraint. So in this case, the ID is the primary key, so that the database automatically checks if at this column there are no allowance for redundant entries. And then you have the name, first name and street. All of them are characters with a fixed limit. So usually databases like fixed limits. Why? Remember the database organization or the data organization. If you have fixed limits in the records, you waste additional overhead of maybe not filled elements or characters, but you have always the same record length, and therefore the search is much easier to manage. So in this case, name is not null. You have a special constraint. Sorry, I mixed it. You have a special constraint, not null. And this means that it's not allowed to have an empty element there at this column. So let's change to the sample. This is this web page from W3 Schools. And I just copy and paste my create table command. So there are different types which you have to learn, but I focus on the main types here. So you enter here the command, the statement, and then you push run, and then you will see that students was created. You can also alter the table later on. So if you forgot some, let's say, columns, so that the table has two less attributes, then you can alter the table. So it's always the same structure. You can create, alter, or drop things. Create is the first creation, alter is changing an existing element, and drop is deleting the whole stuff. And then it's followed by what you want to create, alter, or drop. So in this case, create table, alter table, drop table. And then you tell what the name of the create, altered, or dropped table should be. So in this case, if you alter table, you write alter table students, and then you want to say add or drop. For example, add email with this type. And if you want to drop the email, then you write drop column email. W3 School has some problems with this drop command, so therefore I don't show it here, but usually this is the syntax. And then if you want to delete the students table again, then you make drop table students. So the next important thing is that you can create some constraints. So for example, that the students table has a connection with a foreign key to the residence table. So then you write constraint student residence with a foreign key to residence ID. This is the connection point to the primary key here in this table. Reference is residences residence ID. So residence ID has a connection to residences residence ID. Okay. And of course you have to set here then the correct ID. So this is the primary key for this table. And you can set other constraints like that the foreign key is city zip. Okay. The most important thing is that you have to enter and request data. I jumped to the slides with a insert command. Select is here before the insert because select is the most important thing which you can do if you have just the select rights. But I want to insert a student into our new created table. So let's jump again to our sample in W3. So I have to write insert into students values. It's like a normal sentence. And then I can write the values which I want to enter. So the ID, for example, I give ID like this. It's dependent on the type if you have to use the single quote or not. Single quotes are like in MATLAB, the characterizations for character strings. And then let's say it's Smith Betty. And then we have the street. Nice street 1. Okay, if we enter this, then students has now one additional record so that we can request it. If we push this here, then it does a request automatically. So the request is shown here, and then we get the result. So we have already one inserted name here. So we can do this again. So that, for example, we insert again a person into students values, and then we give a new number and a new name, like my name, Neidhart Alexander in the test street number 10. And if you run this, then you have two entries, and if you push here again, then you see these samples. So as we have now data in our table, we can go back to the select mechanisms. So if we want to select data from the table, we already saw the mechanism. If I pushed on the students table, it did it automatically. So select asterisk from table asterisk mean that we select all attributes, so all columns from students, and then we get the output. If we just want to select special names, so if we want to select only records with the name Smith, then you can also search for this. Now we don't search for the primary key, we search now for the for an additional attribute. And we also can select special attributes so that we do the name, first name from students instead of the asterisk to get the result. So select name, first name from students, where name is Smith. So in this case, we do all of this. So let's have a look into the different methods of combining data. And here you see that it is a restriction and a projection what we did here. So all of these things will appear in the SQL language. You can do, of course, also a connection of a logical combination. So, for example, if you do this, you can say select name and first name from students where name is Smith and first name is Betty. So let's do this in the sample. So we do a select from students. I don't do a selection of special attributes, and where name is equal to Smith and first name is equal to Betty. Usually you end up with a semicolon, so therefore you should directly always enter it. So here we found one result. If you continue with this, you can also have an AND or an OR combination, so as normal logic, or you can have a NOT combination. So all of the logical operators can be used, so AND, OR, and NOT, of course. So in this case, AND first name is Betty, OR name is Ward, so that you have Smith or Ward available, and here you have not the name Smith, though all other names. And you can have special functions. So there are special functions which directly work on the individual items or individual attributes. So for example, you can get the maximum of all IDs. It just works on the integer values, things like that, so that you get the maximum of ID in students or the minimum of ID. You can count the number of students, and you can get the average, and you can get the sum of all results. You can also make combination of that, so that you have additional functions, and you can also reduce the output so that you just get the first one found. For example, select asterisk from students, limit 1 tells you that you get the first match, or you get the first 5 matches if you have limit 5. You can also give a special order like descending or ascending. So if you have a list of names, then you can do a descending or ascending order in the output. It's also quite helpful if you directly want to use the data later. Again, reminder that this is taken from W3 schools. A reminder is this inner join, left join, right join, and full outer join. These things are supported. The most important thing I would say is the inner join, which is just the join where you have two tables and you get the intersection of these two tables. And this is done with this structure. So if you have these 3 tables, you have the table student in course, university course, and students. And then you want to make this intersection, this join. And then you can make select, and then you name the table dot the attribute, so students dot name. So you take students dot name this attribute, this column, then students first name and university course title, and then you say from students, university courses, and student in course. These are these 3 tables, so you have to tell the database management system which tables you want to use, and then you have to select where university course ID is equal to student course dot course ID, so where this ID is the same like this ID, and student in course student ID is student's ID, and student's name is Smith, so that you have the same course ID here, and you have a connection directly to here. This means that this is the connection table, this is this relation, and this relation appears here and here. And this makes the connection from the left table to the right table. Okay? So you always identify the table and then the dot, and then the attribute of the table. And here you also select a special reduction of the data. So this is the usual join which you can use, so that you get a combination of students and university courses. And you will get all of the courses where one specific student, here the student Smith, is in. You can train this all in these W3 schools, and then you can play with it. We already did the insert, so I don't take too much care in this. You can also update the information. For example, if you have the value available, if you have already a record and you want to change this record, for example, then you tell update students. You always tell what you want to do, the same stuff as before. Update the table students, and then set the ID to this, where the ID was this. So we change now the 114423 to 124423. So we set it to this new where the ID is this. So we have to use this where item because we have to select one individual record and we have to identify this record. Of course, we can delete a complete record. So in the same style like before with the tables, delete from students where ID is this. So we do a selection and then we delete things. We can also make transactions. Transactions are a sequence of different individual commands, SQL commands, usually separated with a semicolon. So you can, for example, do insert into students' values, insert into student values, and after writing the whole stuff and starting the run button, all of these things are done in one step, which is not interruptible. So it's an atomic step, and therefore you can also do a select and also an update in this style. So you can set a combination which is non-interruptible, and modern databases also allow to do a rollback, so that, for example, it's not directly available. You can roll back to the previous state of the database, which was before you did the transaction. All of these commands can be tested in this W3 Schools web page, which helps you to play with this data even if you have no database, no access to real database. You just have to deal with the advertisement there, what is a little bit a pity, but of course that's web pages must be financed, and therefore they use this. So the SQL language which I presented was quite fast here. Therefore, we will have the tutorial. In the tutorial, we will train this a little bit more so that you play with this W3 stuff again, and we will train this again. For now, we are finished with databases. You learned everything about what is a database, how to design a database for a beginner with this relational concept, so that you have a normalized structure, you have relations, you have 1-1, 1n or nm structure, and you also saw the basics of SQL. SQL is quite simple, I would say. If you have the idea, or if you use this paradigm of the data sets, the mathematical data sets, then it's quite simple to use, and it's like writing real statements or commands. So drop, table, blah blah blah, insert value, and so on, or insert into table values, blah blah blah, things like that. So it's just a little bit of training, and most databases offer real nice APIs, so that you have programming language libraries for different databases that you can directly use these SQL statements to get data from the database over a standardized communication interface. That's it. We'll see each other in the tutorial. Please stay safe and keep prepared for the rest of the classes. Bye bye.